Honeycomb structure. 3. Flocculent and dispersed structure. Single-grained structure. Cohesion-less soils, such as gravel and sand, are composed of bulky grains in which the gravitational forces are more predominant than surface forces. When deposition of the soil occurs, the particles settle under gravitational forces and take an equilibrium position as shown in figure 3.9. Each particle is in contact with those surrounding it. The arrangement is somewhat similar to the stacking of oranges on a grocer's counter depending upon the relative position of soil particles. The soil may be a loose structure or dense structure. Honeycomb structure. It is possible for fine sands or silts to be deposited such that the particles, when setting, develop as over large voids in the soil mass. Figure 3.10. The honeycomb structure usually develops when the particle size is between 0 or 2 and 0.02 millimeters. Dispersed clay. The final structures of clay are established from the balance of interactive forces and external forces applied to the clay assemblage. If the final interparticle forces are repulsive, particles want to separate from each other when the boundary confinements are removed. This is the situation of dispersed clay. The soils in dispersed structure generally have a low shear strength, high compressibility, and low permeability. Flocculated structures. If the internal particle force are attractive, then particles want to come together, making flocculated clay. If the edge charges are positive, most likely the edges are attracted to the flat surface of other clay particles. This makes a cart house structure of flocculated clay, most commonly in saltwater environment. In freshwater environments, more face-to-face structures are formed due to negative charges at the edges. There are 3 types of clay minerals: kaolinite clay, montmorillonite clay, Eller clay. Silica C occupies the center positions in oxygen ions O are strongly bound core atoms. Silicate tetrahedral sheet is symbolized with a trapezoid, of which the shorter face holds electrically unsatisfied oxygen atoms and the longer face holds electrically satisfied oxygen atoms. इन सभी मिट्टी के खनिजों में 2 बुनियादी परमाणु शीट है: सिलिका टेट्राहेड्रल शीट 2। सिलिका टेट्राहेड्रल शीट में एल्यूमिनियम टेट्राहेड्रल शीट सिलिका सी केंद्र की स्थिति में रहती है और ऑक्सीजन आयनों एक और परमाणुओं के लिए दृढ़ता से बंधी होती है। सिलिका टेट्राहेड्रल शीट को ट्रिपजॉइड के साथ गया है, जिसमें से छोटा चेहरा विद्युत रूप से असंतुष्ट ऑक्सीजन परमाणुओं को पकड़ता है और लंबे समय तक चेहरे को विद्युत रूप से संतुष्ट ऑक्सीजन परमाणुओं का सामना करना पड़ता है। In aluminum octahedron sheet, aluminum ion positioned at the center and hydroxyl ion O bonded to the core atoms. Aluminum octahedron sheet is symbolized with a rectangle with top and bottom faces having the same characteristics of exposed hydroxyl ions. Figure 3.1 gives the atomic structure of the above 2 basic sheets. Clay. The basic unit of this type of clay is formed by atomic bond of the unsatisfied face of silica sheetonite. The face of aluminum sheet is seen in figure 3.2. The bond between 2 sheets is strong as primary bond. However, the stack of 2 sheets is not a form of clay yet. Many layers of basic kaolinite unit make a kaolinite clay. If 1 unit is about 7.2 angstrom. Kaolinite clay. The basic unit of this type of clay, the unused face of a aluminum sheet of the silicon. The kaolinite clay structure may attract the unsatisfied face of another silica sheet to make a 3-layer stack, and shown in Fig 3.4. This makes the base morelinite clay structure with the thickness of about 10 angstrom. The link is due to natural attraction for the cations in the intervening space and due to van der Waal forces. The negatively charged surfaces of the silica sheet attract water in the space between two structural units. This results in an expansion of the mineral. The soil containing a large amount of the mineralonite exhibits high shrinkage and swelling monomer characteristics. Mineral basic structure of this clay is the same as the one of morelinite. However, potassium ion K+ are filled in between facing O2 and O2 surfaces of silica sheets as seen in Figure 3.6. The characteristics of this clay are classified as in between those of kaolinite and morelinite.